March, and we will start with a talk by Haochang Jiang. I hope I pronounced it not too far away from reality.
Yeah, perfect.
Okay, so you can start sharing the screen. He's a PhD student at the University of Tsinghua, and he will be talking about the survival of ALMA rings in the absence of pressure maxima, I guess, in disks. So,
yes, thanks for the introduction. It's my great pleasure to give talk here in the amazing meeting. So my name is Haochang Jiang. I'm now a PhD student in Tsinghua University in China. So the title of my talk is Survival of ALMA rings in the absence of pressure maximum, but I'd like to change it a bit because I found everybody is talking about all kinds of ALMA rings. So it's more precisely should be the survival of dust ring in proton blandisk disk in the absence of pressure maximum. So the slides I'm showing here is amazing D-sharp result. Well, this amazing project target 20 proton blandisk and resolve them down to 5 AU resolutions. So in this amazing beautiful pictures, we can see that the ring and gaps substructures are everywhere. So it's existing every disk, every source they target, and it's really very amazing. So it's very natural to ask, so how these ring and gaps are formed. In order to understand the forming of these rings, so we need to highlight that what we're looking at is the thermal emission from these pebble-sized particles in the proton disk. So we want to know the original of this ring. We need to learn a little bit about the dynamic of these pebbles. So like the illusion shows here, if there is no gas in proton disk, these pebbles should perfectly follow the capillary rotations. But because of the pressures, because of the gas in the disk and the gas has pressures, so the gas actually is slower than the capillary rotations. And therefore, for pebble inside the proton disk, they will feel a headwind from the gas. So they will drag back the gas and lose angular momentum, so spiral towards the sun. And for such a procedures, you will have a radial velocity as an equations described here. So the three most important parameter here is the Stokes number, which is just the size of the particles, aerodynamic size of the particles. And so the bigger particles, they usually should drift faster. And also the local concentration will influence the dynamic of it. I will explain it later. And what's the most important is the pressure gradient, because as you can see here, it will define the sign of this equation. So the natural result is these pebbles should follow the pressure gradient. And as this nice picture shows here, so particles will trapped when you have a pressure maximum in the proton disk. This is the animation to show such a procedure. So the y-axis is the surface density of the solid, which is in the solid lines, and the gas, which is in the dash lines. So we impose a gas pressure bomb cell. And so initially we don't have any substructure in the dust, but as time goes, this dust will accumulate inside these pressure bombs and form a ring structure there. So from ALMA, if we see such a structure, we can expect to see a dust continuum ring here. Such a pressure bump is a natural outcome of the planet gap opening process. So if we do have a planet inside the disk, it will push away the gas in the vicinity of it, as you see in the animation. So you will naturally get a pressure bump at the outer edge of its gaps. And we will naturally ask, so does this pressure bump really exist in the proton disk? Before, we don't really have such a high resolution to resolve the gas structures, but last September, the wonderful ALMA big project program maps come out. So well, they target 5 sources to have a very high resolution, so as high as the D-sharp to look at the substructure in this chemical line emissions. So here we can say that the ring and gaps are also everywhere in this gas component of this disk. So let's pick one specific species, which is CO. So by proper thermophysical modeling, you can guess the CO gas radial profile as shown in the top left panel here. So which you can see as this. And we'll identify a gap here, you're just filling it by this shadow, and so well for this dust continuum, you can also get a dust surface density and filling it by some more deeper blue shadows. So if you if you extend this into lines, and for all of its 5 sources, you can always do such a procedure, and you will get plot like this. And if we just use the very direct ICE identifiers, we found that there is quite a large fraction of dust rings actually do not really coincide with this sail bump. So at least maybe sail is not a good tracer, or maybe something else is wrong, but maybe the dust is not really coincide with the gas in the bump regions. So furthermore, as this morning, the talk by Charles Laws, so he has a great job on these substructure identifications, and they pick up more than 200 ring and gaps in this line emission momentum zero maps. And what they do is, I just borrow a picture from his presentation. So they know the peak of this gap and ring in the line emission maps, and they know the ring and gaps in the continuum maps. Therefore, they can comparing these correlations or overlap fractions quantitatively. So this is the result Charles showed in the morning. And we have a further naive question on this. So what if we replace these observed chemical features randomly? So I say it's randomly, but of course we need to assume a random distribution here. So we indeed do this, and we get such a result. So we know the number of the features we observed. We know the inner edge and outer edge where we can see them. We just randomly put them among the disk and to say the correlation, and therefore we should get a distribution as this violin plot shows. So the y-axis is the fractions. So the chemical substructure can coincide with the dust substructures, and the violin plot show the probability distribution function. So you can imagine that at the at each violin plot, you will have the highest probability to get such a overlap fraction. And you say this observed overlapping fraction is perfectly fat with a random distribution. So indeed, we have some outer layer here and here, but in general, we can say we do not say a universal correlation between this continuum ring and gaps and the line emission ring and gaps. So we propose that probably this pressure bump is not the primary supporter of such a ring and gaps formation in the dust component. So we ask questions. So can the dust ring survive without this pressure bump support? And the answer is, of course, yes. So in the rest of this talk, I'd like to introduce the clumpy ring model we built for explain such a dust rings without these pressure bumps. So here is a sketch of our clumpy ring models. So first, as the very standard model, we impose the pebble who is radial drift from the outer region, which is on the right of this plot, to the inner region of the disk. So the pebble will first have an individual drift, but additionally to this disk pebble, we introduce another component, so-called clump pebbles. This clump pebble is just be reflect on the ring when we observe it. So how it works? We simply say, okay, these two components can diffuse and settle between each other, so they can exchange. But when the dust to gas ratio locally, volume dust gas ratio is larger than unities, because of a mechanism of so-called streaming instabilities, you should see such a filament structure in the protomagnetic disk. So this is the simulation from Haochang Jiang's papers. So we can look at the protomagnetics. If we look at its edge, on the wedge view, it's just like a circle, like a cone. And if we look from top down, a top view will have a filament structure, just like the rings. So we also self-consistently say this high density regions can collapse into planetesimal, which is much bigger kilometer size dust rocks, and they can diffuse towards just towards outer region, also inner regions. So there's no magic here, but just go back to the equation for the radial drift. So we just increase the local concentration, as you can see. So if this Z is very large, this radial drift will also very low, and therefore it will just have a traffic jam in the proto-magnetics and has such a dust clump and ring feature. So here is the simulations to show such a scenarios. So we do impose a tiny perturbation in the proto-magnetics at 10 AUs, and we don't introduce any other extra gas surface density perturbation, but just let it evolve. And you can see here, this dust density will have a power out, and which is propagating to the outward regions, and also it form a loss of planetesimal, which is the seed planet behind it. We investigate a large parameter space for such a mechanism. Well, the x-axis is the Stokes number, as I mentioned before, is just the aerodynamic size of this particle. So the larger the Stokes number will also be larger, and also the external mass flux. So this survival ring is just a fact that we have larger external mass flux to support the ring than this mass that's leaking from the ring region to the inner region. So once if we have the external mass flux larger than this, the analytical predict leaking mass flux, we will have a ring to survive. And as you can see here, the ring feature show various results, which can have very high contrast to the background regions, or it can be very thin. We specifically pick two sources in the D-sharp program, which is the ES22, which is a single ring disk, and also the AS29, who show at least two very sharp rings in the outer regions. So here is our simulation result and the mock image of the models, and you can see it's fit quite well of the observation. And so you probably want to ask, so what's more about these models? We also found that if such a scenario indeed happens, and we know that well, naturally require that the pebble density inside the ring should be very high. And as we already described, because the Z is very high, so the radial drift is also very low. And such a case well perfectly meets the requirement for pebble equations. So therefore, we propose that probably this ring are not an egg of this planet, but it could be a chicken, so to produce a planet. We have a manuscript on this topic in preparations, so hope to it will come soon here. And here is my take-home message. So first, we don't find any statistically significant correlation between this continuum and line emission substructure in the 5 sources of the MAPS large program. And second, we build a clumping ring model to explain the dust ring we observed in ALMA's image without a pressure bump to support it. And finally, we propose that this clumping ring actually could be a good place for the planet formations. I leave my presentation here, and I'd like to take any questions. Thank you.
Thank you so much for this, I would say, really clear talk, at least to me. So thanks a lot. And for bringing this point of discussion between traditional methods and maybe this new approach. So I have some questions, but I wait for people maybe writing in the chat. So Marcela.
Yes, there is a question. Thanks for the very nice talk. You showed the model with accretion rate with 10 to the -9 solar masses per year. Is the accretion towards the disk? Have you tried with higher accretion rates?
That's a very good question. So of course, in the real case, we should have a dissipation in the accretion rate, but in our study, we do not vary the accretion rate. So it always has a constant external mass flux. But let's look at this figure. So you can imagine that if for the same Stokes number, you decrease the external mass flux, the ring will fading away. But that's well requires million years time scale. So the ring can still survive for some years. So yeah, we do not do this, but in reality, we should consider such an effect.
Okay. So I think for the moment there are no more questions in the chat, but I have some more questions. So while people write, so I take the time to ask something. So one that I guess I know the answer, but so in the simulation you showed that over time, so this ring would be moving outwards in the disk, right? Is this something that, so I have two questions here. Is this something that could be detected over which timeline base?
Yes and no. I'm not quite sure we can really detect this, since the mechanism of such out moving is not really the pebble are moving outward, but because the front of the ring is moving outward. So it's a phase velocity. It's just simply like, so you always have new power up at the outer edge of the ring. So materials always power up at the outer edge, but they are always have a velocity directions towards the sun. Okay. So the phase velocity of such a ring will move outward, but the real velocity is still inward. So if this phase velocity movement can be detected, then the answer is yes. But I think it's very hard because the velocity is also very low. It's probably 10 centimeter per year around this. So I'm not quite sure it's detectable or not, but if the answer is yes, it will be very exciting.
Yeah. I have another question. Can I ask Marcella, or are there, I think
there was a comment by Vijay. I had asked the question in the morning along the same lines, and I was told that there are some results incoming about time evolution of the rings. See Charles Low's talk and Slack answer. So it's just a comment.
So maybe we have something, or maybe it's more related to the different time stages of the disks. I don't know.
Yeah, maybe.
I have, so since I have a little bit of time still, so we have time. You mentioned that to have this this ring forming, you need a dust to gas ratio higher than 1, right?
That's true. The volume dust to gas ratio higher. So at the mid-plane region.
Would this mean that we should observe that these rings are forming there in the places where there are gaps in the molecular emission, or we could be tricked in the observations? Because from, maybe I'm confused, but I would expect from what you say is that the amount of gas would be much lower, and therefore we should see that these rings are matching nicely the places of depletion of gas. Is this correct, or is this wrong?
I think that's a good point of view. I'm not quite sure because so for our model, the pebble is always in a very thin mid-plane regions. So the skull height of dust and the gas could differ maybe 10 times. So I'm not quite sure. Maybe it's true, yeah.
Okay. Yeah. So I have more questions, but I don't know if you keep asking or just last one, since we have, I think it's very short, and I see that no one has written in the chat yet. So this, you would then say that this formation of these rings would be, or the accumulation of these pebbles in the mid-plane, this is completely random. So it can happen anywhere in the disk, and as soon as it happens, if we reach this condition, then the ring will form. So
yeah, that's true. And I can show you an interesting animation here. So while we test a very extreme case, as you can see here is sorry. Oh, I cannot run. I want to play this video. So this is a very extreme case. So while the ring can form at inner 10 AU, and you can say it's just move outward towards 30 AU and disappear, and it will cycle it. So once you meet such a Z equal to unity, you will power up as a ring, and it's spreading outward. And when you fail to it, you will disappear, and you release the material to inner region, and you form it again and again. Okay. So it can indeed happen anywhere in the disk once you meet the requirement. Okay.
Yeah, thanks a lot. Thanks for answering all the questions that I have a few more. I will probably post them on the Slack.
You're welcome.
Thanks for the animations and for the talk, and